Hello everyone, in this video I will teach you how to design a square footing. Let us start with a question. A square footing has to transfer a load of 1000 kN from a square column of 400 by 400 mm. Assume M20 concrete and Fe415 steel and SPC of soil 200 kN per meter square. Design the footing and sketch the reinforcement details. So this is the question that is given to you. Now let us write the data that is given in the question. Here the axial load which is carried by the column over the footing is given as 1000 kilonewton. Let us consider capital P be the axial load from the column which is coming over the footing, that is as 1000 kilonewton. And the size of the column, it is a square type of column whose size is of 400 by 400 mm. Here the value of both B as well as D is 400 mm. Then the grade of the concrete as well as the steel is given to you. Here the value of FCK is 20 Newton per mm square and Fy is 415 Newton per mm square. Whereas the SPC of soil at which the footing will be resting is given as 200 kilonewton per meter square. Now with this data we had to design the square type of footing. Let us start designing it. The first step is to find the total load which is carried by the footing. So here there will be two types of loading which is coming from the footing. One is the self weight of the footing itself, other is the column load which is coming over the footing. Here we will be assuming that self weight of the footing as the 10% of the column load. Here if you take 10%, then in the terms of fraction you need to write it as 10 divided by 100, and the load which is carried by the single column is of 1000 kilonewton, and 10% of 1000 gives you a value 100 kilonewton. Then you have to write the column load here which is of 1000 kilonewton. Then add both the readings. On adding both the values you will get the total load which is carried by the footing, that is of 1100 kilonewton. So that completes step number 1. Let us move to step number 2. In step number 2 we have to find the size of the footing. So to find the size of the footing, we first have to know what is the area that we need to design. So to find the area which is required for the footing will be given by the formula load by SPC. So load is the total load which is carried over the footing, and the SPC of the soil at which the footing is resting. Here we got the total load of 1100 kilonewton and the SPC of the soil is of 200 kilonewton per meter square. On dividing those two values we get a value of 5.5 meter square. This much amount of area is required for a footing. Now from the area let us know what is the dimension of the footing that is required. Here as we are designing for the square type of footing, both the values of L will be equal to B. Hence I am directly writing L is equal to B as square root of A required. We got the A required as 5.5. On putting square root for 5.5 we will be getting a value of 2.345 approximately, which is equal to 2.5 meter. Then finally at the end let us whatever the things that you have designed, you mention it with the sentence as provide the footing size of 2.5 by 2.5 meter. Now if we are providing the footing size of 2.5 by 2.5 meter, then the area what we have provided has to be find out. So for finding that, let us multiply again L with B. Both the values are 2.5 and 2.5. On multiplying 2.5 with 2.5 we will be getting a value of 6.25 meter square. So this is the area what we have provided. The required area was 5.5 square, but we are providing much greater than that. We are providing an area of 6.25 meter square. So that completes step number 2. Moving to the next step, the step number 3 is to find the net upward pressure. So that is denoted with the symbol small q. To find the net upward pressure we have the formula the load which is carried by the column divided by area what we have provided. So the load which is coming from the column is given directly in the question, that is of 1000 kilonewton, and we have provided an area of 6.25 meter square. On dividing these two, we will be getting a value of 160 kilonewton per meter square. Now we have to check this value with the given value of SPC of soil in the question. The given value of SPC of soil is 200 kilonewton per square, and we got a value of 160, which is lesser than 200. So if net upward pressure comes less than the SBC, then whatever the design or whatever the size of the footing that we have provided, that is safe. Finally, you need to mention it as, hence the design is safe. So that completes step number 3. Let us move to the next step. In step number 4, we will be finding the bending moment which is acted on the column. So to find that, we have the formula M is equal to Q into B into half of L minus D divided by 2 whole square, where small q represents our net upward pressure, capital B represents the width of the footing, L represents the length of the footing, and capital D represents the column's depth. So now one by one we will be substituting those values in the next step. 160 into 2.5 into 1 by 2 into length again is of 2.5 meter minus of D. Capital D is the depth of the column. The size of the column is given in the question, that is in terms of 400 mm. If you convert that in terms of meter, you get 0.4 meter, then that divided by 2 to the power of 2. So now on solving the whole thing, you will be getting a moment of 220.5 kilonewton meter. That is our working moment, from which we had to find the factored moment. So let us find the factored moment by multiplying our working moment with the factor of safety 1.5. On multiplying our value with 1.5, we will be getting a moment of 330.75 kilonewton meter. So that completes the bending moment calculation. Let us move to the next step. In the next step, we have to find the depth of the footing. So for finding that, we first have to assume the section of our footing is coming under the balanced section. In the balanced section, both the ultimate moment will be equal to the limiting moment. So by considering that condition, we had to adopt the limiting moment value formula for Fe415 grade steel, and the formula is 0.138 FCK into BD square. Now from this formula, we will be extracting the formula of D as square root of mu divided by 0.138 FCK into B, where mu is your factored moment, and the value what we have got is 330.75, that is in terms of kilonewton meter. You multiply that with 10 power 6 for converting that in terms of newton by mm. So then divide it with 0.138, and then FCK is the grade of concrete, that is 20. B represents the width of the footing, that is 2500 mm. We got 2.5 meter width here. Again you convert that in terms of mm. On converting, we get 2500 mm. Then on simplifying the whole thing, we will be getting a value of D as 218.94 mm. So which is the depth of the footing. But we are not keeping this much of that, because if the shear consideration also has to be coming into picture. If we consider the shear forces which is acting on the footing, then there is a less possibility of resisting the shear forces here. So for that point of view, we will be increasing the depth twice here. So whatever the value that you get from the calculation, you just do twice of it. So twice of our value gives you a value of 437.88. Approximately you take a value of 440 mm. So now this is the depth what we are providing. So 440 mm represents our effective depth of the footing. Now from this effective depth, let us find the overall depth of the footing from the formula. We know that overall depth is equal to effective depth plus effective cover. If the effective cover is not given in the question, you yourself can adopt a value in between 40 to 60 mm. Here let us adopt a value of D dash as 50 mm. We are assuming a value here as 50 mm, and let us add 440 with 50. We get the overall depth as 490 mm. So that gives you the depth of the footing. Moving to the next step, in step number 6, we will be designing the steel reinforcement here. So for designing, we have to take the formula of bending moment, that is the ultimate bending moment, and the formula is 0.87 Fi ASTD into 1 minus AST Fi by FCK into BD. So I am extracting the formula from IS 456 2000 of page number 96, I think. or 96 or 93. So now we got the value of mu, that is of 330.75. You convert that in terms of Newton mm. We need to keep always mu in terms of Newton mm itself. This is equal to, you substitute rest of the things, and then you simplify the whole equation as a single unit. I had done this calculation in the previous videos. You can refer those videos for in order to get the calculation of the AST at a time in the form of equation. Now if I solve the whole equation, I will be getting a value of AST as 759.59 mm square. Now we have to check whether this AST is getting satisfied with the minimum AST or not. So in order to check that, let us consider the minimum AST value as 0.12% of our gross area. Here 0.12% is written in terms of divided by 100, and our gross area is B into capital D, where B represents the width of the footing and capital D represents the overall depth of the footing, that is 490 mm. Now on doing the calculation of this, we will be getting a value of AST minimum as 1470 mm square. That means for a footing size of 2.5 by 2.5 meter, this much amount of area of steel has to be provided. But what we are providing or what we are getting here is 759.59, which is much lesser than this. Hence you cannot provide this much of area. Hence for that reason, let us go with the minimum AST itself. So this much amount of AST has to be provided for a size of 2.5 by 2.5 footing. Now by considering AST minimum as our provided or as our required AST here, let us assume we are providing a 16 mm dia bars, or we are using 16 mm dia bars within the footing. Now by considering that, let us find the area of one bar. To find that, small AST is given by pi d square by 4. It is a formula. So pi into the dia is 16 square divided by 4. On solving this, we get a value of 201.06 mm square. Now let us find the spacing that has to be provided for the footing. From the formula, SV is equal to small AST by capital AST into capital B, where small AST gives you the area of one bar, capital AST gives you the total area which is required for the footing, and B represents here the width of the footing. Whatever the values that you have found, same values has to be written here, where the value of B is 2500. We always have to keep B in terms of mm whenever we do spacing calculation, because each and every term will be in terms of mm itself. Now on simplifying the whole thing, we will be getting a value of 341.94 in terms of mm. That means if we are considering a 2.5 meter width, for 2.5 meter width of the footing, the spacing what we had to provide is 341.94. If that is so, then what will be the spacing that has to be provided per meter length of the footing? For finding that, we had to divide our value with the length of the footing, that is 2.5. On dividing, I got a value of 136.77. Let us consider approximately equal to 130 mm. So whatever the calculation that you had done so far, you just mention it at a single sentence as therefore provide 16 mm dia bars at 130 mm center to center. So that gives you the design of the main reinforcement, and that completes step number 6. Let us move to the next step. In step number 7, we will be designing for the shear. So here we will be designing for both one way as well as two way shear. So for one way shear, we had to consider the critical section. The dotted lines represents here critical section. Whatever the part that is coming beyond the dotted lines, the hatchet portion is coming under the critical part. That means the shear will be maximum affected by this portion. So we can say that the critical section is acting at a distance of small d. That means it is acting at a distance of the effective depth from the column face. From any one side of the column, the critical section will be acting up to distance of d. So now let us find the shear force from this. So to find the shear force, we have the formula V is equal to Q into B into L minus D by 2 minus of D. Here I am doing L minus D, means L represents the whole length of the footing. If I but I am interested on only from the center of gravity to the critical section here. See, I am only concentrating from this here to here. So I only want this much of distance. The distance will be found out by the total distance. We first do the half of the distance here. This is our total distance. Then from this total distance, let us subtract this value. This is again d by 2. So L by 2 minus d by 2. So I took 2 common here. If I take 1 by 2 common, I will get L minus d. Then minus of the remaining distance. If I do L by 2 minus d by 2, I will be getting this of this minus this gives you this much, and then you subtract, the remaining will be this. This is minus d. Sorry, here I am taking the distance this, and then this, and then this. These three distance I need to take at the corner from the corner of the footing here, because my critical section is acting at the right side. If my critical section acts as the left side, whatever the calculation that I have said earlier, that was correct. Now the first distance represents the half of the length. Then the second distance represents the half of the distance d. Then the third distance represents our effective depth d itself. L by 2 minus d by 2 minus d. L by 2 d by 2, I took 1 by 2 common, and hence I wrote the formula as L by d minus L minus d by 2. That minus of remaining distance is d, because I need the whole distance from the critical section to the edge of the footing here. So that gives me the total length of the footing which is left out beyond the critical section. Now, so let us substitute all the values one by one in the next step. The value of upward pressure is 160. The width of the footing is 2.5. Here all the terms has to be kept in terms of kilonewton and meter itself. Then the length of the footing is again 2.5. D represents the size of the footing along the horizontal direction, that is of 400 mm. You keep it in terms of meter, that gives you 0.4. Divide it with 2. Minus small d represents the effective depth, that is of 0.44 meters. Now simplify the whole term. On simplifying, you will be getting the value of V as 244 kilonewton. So that gives you the working shear force. Let us find the factored shear force now. To find the factored shear force, let us multiply our value with 1.5. So on multiplying, we get a value of Vu as 366 kilonewton. So that gives you the shear force value. Now let us find the nominal shear stress from the formula 2V is equal to Vu by Bd, where Vu is our factored shear force. Just now we found the value, that is 366, which was in terms of kilonewton. Let us keep it in terms of newton by multiplying it with 1000. Then divide it with B. B you have to take it as capital B, that is your width of the footing, that is 2500, into D. D represents your effective depth, that is 440. On simplifying, we get a value of tau V as 0.33 Newton per mm square. Then let us find tau C. Before we do, the value of tau C will be depending on our percentage steel. So for which we first have to find the percentage steel value here. To find the percentage steel, we have the formula 100 AST provided divided by BD. So now this time we have to take the value of provided AST, not the required one. So we didn't know what is the provided AST is. Let us start finding the provided AST. What we have provided is found out by the spacing equation itself. The spacing formula was small AST by capital AST into B. Here I am just interchanging the value of SV and AST here. On interchanging, I will be getting the equation of AST as small AST by SV into B. The small AST represents our 1 bar AST, that is area of 1 bar. What we got is 201.06, and the spacing what we got is 130 mm. Into width, you have to keep it as 1000, because we have got the 130 mm spacing for 1000 mm width of the footing. So that gives you the AST provided, which is of 1546.62 mm square. The same value you have to keep here. Divide that with B. as you are keeping the AST provided for 1000 meter length, length, the same length you have to keep here, 1000 itself we need to keep, that into 440. Then you simplify the whole thing, you will get the percentage steel value as 0.35%. Now we have to find the percentage, the value of TOC, that is design shear stress, from the percentage steel. Let us check we are getting the value of 0.35 from the code book directly or not. So for which we had to refer table number 19, page number 73. So let us go with the code book here. Here in this code book, the first column values represents your percentage steel value, whereas the rest of the column values represents the TOC value for the particular grade. So here in the question we have a grade of M20 and we are searching for the TOC value of 0.35 percentage steel. So now let us see, do we have 0.35 in the first column? We have 0.15, we have 0.25, we have 0.5, 0.75, but we don't have 0.35. Then let us search in which two readings 0.35 will come. See, our 0.35 value comes in between 0.25 and 0.5. So now what we have to do means, we have to first write the value of TOC for 0.25. See, the value of TOC for M20 grade concrete and for steel of 0.25 is 0.36. Then we had to write it for 0.5 percentage steel for the same grade. For 0.5 we have the TOC value as 0.48. That is what I have written here. The first value is 0.25, TOC is 0.36. For 0.5 the TOC is 0.48. Now we are searching a value of TOC for a steel percent of 0.35. So let us name it as X and let us keep 0.35 in between those two values. Now let us start finding the unknown value X here from the linear interpolation method. So while doing the interpolation, what I am doing here, I will be first considering the PT values, the highest PT value minus lowest PT value. Then I will be dividing that with the highest TOC value with the least TOC value. Then that is equal to, then second highest PT minus of least PT divide by second highest TOC minus of least TOC. Then we go on simplifying it. I have simplified the whole LHS term. Then I got 2.083 on the LHS side. If I simplify the numerator, I got 0.18. Divide that with X minus 0.36. Then we cross multiply it. On cross multiplying, I am keeping X minus 0.36 only on the LHS side and I will bring the same 2.083 to the RHS side. Then I divide these two values. On dividing these two, I got a value of 0.048. Then I am only have to find the value of X here, for which I need to keep X here and I bring minus 0.36 on the RHS side. Then addition of these two values gives you a value of 0.408. The value of X itself represents the value of our design shear stress TOC. Therefore, we can write the value of TOC as 0.408 Newton per mm square. Now let us compare the value of TOV with TOC. Nominal shear stress has to be compared with the design shear stress. On comparing, we will be getting the value of TOC which was 0.33 and value of TOC is 0.48. On comparing those two values, we can assure that our TOV is less than TOC. If we are getting TOV as less than TOC, whatever the design that we had done so far, that is safe against one-way shear. Then let us check it for two-way shear. For checking the two-way shear, now we will be considering the punching shear or the critical axis will be lying at a distance of d by 2 from the face of the column or on all the four sides. So at all the four sides, the distance is d by 2. So the dotted lines, what you can see within the footing, that represents our critical section. And here the length of the critical section is given as A0 and the width is written as B0. Let us find those values first. So A0 is equal to, see, d plus d by 2 plus d by 2. d by 2 plus d by 2 gives you small d. Similarly, let us write the formula for B0. B0 is equal to B plus D by 2 plus D by 2. half of the bearing on the either side gives you one bearing. Hence, I had directly written the formula as B plus D. Now, what is D representing here? The capital D represents the width of the column, which is of 400 mm, that is 0.4. Plus, small d represents our effective depth, that is 0.44. Let us add those two values, we get 0.84 meter. Similarly, B represents our depth of the column here. One more length, or the side width of the column, that is along y axis, we can say, that is 0.4, plus effective depth is again 0.44. On adding these two, we will be getting the same value of 0.84 meter. So then we find the shear force value from the formula V is equal to Q into A provided minus A naught into B naught. Here the shear force value for the two-way shear is different from the one-way. So now Q is nothing but your net upward pressure itself, that is 160, into area provided. Whatever the area that we have provided for the footing that we had to adopt. We have provided an area of 6.25 minus of, you just multiply these two values, A naught with B naught. Then you simplify the whole thing. You will get the value of V as 887.104 kilonewton. Then you convert that in terms of factored shear force by multiplying it with 1.5. So we will be getting 1330.656 kilonewton. Then once you know the shear force value, let us find the nominal shear stress with the formula 2V is equal to VU divided by 2 into A naught plus B naught into D, where VU is kept in terms of kilonewton, but while substituting in the value of tau V, in the formula of tau V, we always have to keep it in terms of Newton by multiplying our value with 10 power 3. Divide that with 2 into, always all the values which has to be kept in the tau V will be always in terms of Newton and mm itself. For that reason, point A naught as well as B naught will be converted in terms of Newton. Millimeter. On converting, we will get 840 and 840. D is the effective depth, that is 440. On simplifying the whole thing, we will be getting a value of tau V as 0.9 Newton per mm square. Then, let us find the value of design shear stress tau C now from the formula 0.25 times of root under FCK. So, we have the grade of concrete as 20. Let us simplify it. On simplifying, we will be getting a value of 1.118 Newton per mm square. Now, let us compare both the values. On comparing both the values, our tau C value is greater than tau V. If we get tau V greater than tau V less than tau C, whatever the design that we have done, that is again safe against the two-way shear. As we are getting tau V less than tau C, we can say that hence the design is safe against two-way shear. And that completes the shear design. So now we are at the last stage of our design. The last step is to check for the development length what we have to provide. So for finding that, we have the formula. We can adopt directly LD as 47 times of the dia of the bar. So we have adopted the 16 mm dia bar here. So 45 times of 16 gives us the value of 752 mm. So that is our development length. Now let us find what is the length which is available within the footing. So for finding that, we have to find the length available as half of B minus B minus of effective cover. We are assuming an effective cover of 50, I think. So 50 here. So for which I am keeping this as 50. So where capital B represents the width of the footing and small b represents the column depth here. So that is from the center, right? See, this is our development length. So whatever the length that is left out or that is available on any side from the center, you can say. So that has to be found out. So from center means we first have to do half of the length. Then we need to subtract that with half of the column dimension. Then with the effective cover. Half length gives you this. That is 2.5 by 2. Then half of the column is this. Then minus of this is effective cover. So that is what I have written here. On simplifying this, I got a value of 1000 mm. So which is greater than the development length. So hence, if the available length is greater than your development length, that means much space is required. We can still extend our development. It means we can still extend our development length here. So if this is so, then whatever the design that we had done, both the length as well as the width of the footing is safe again. So hence we can finally say hence the design is safe. So that completes the check for the development length. Once all the design is done, let us draw the reinforcement details here. Let us sketch the reinforcement details. So we will be first sketching the longitudinal section here. So the longitudinal section of the footing look like this. So we have the column. The outer line represents the width of the column, that is of 400 mm. So within that you need to draw two vertical lines by giving a gap of effective cover of 50 mm. Then you just have to draw one more horizontal line at the edges, and then you drop two vertical lines from those two points, and then you add those 2 points here. So this portion of our drawing represents our footing depth. So this is our overall depth of the footing. So now within the footing we will be replacing our main reinforcement. So the horizontal line what we can see is also the main reinforcement, and what the circles what you are seeing is also our main reinforcement itself. Both we are keeping it as 16 mm dia bars, which is acting at a spacing of 130 mm center to center, and the whole length of the footing is about 2500 mm. So that gives you the longitudinal section of the footing. If you want to draw the plan of the footing, let us draw a square, because we have designed for square footing here. So the size of the square will be of 2500 mm by 2500 mm. Then by giving the effective cover gap from all the 4 sides, you have to draw the vertical lines as well as the horizontal line. It is not necessary that you have to keep it scale and you have to measure 130 mm exactly, because we just have to show the reinforcement details here. For that purpose I am drawing 4 or 5 vertical lines and the remaining horizontal lines. Both the horizontal direction or the vertical direction, the bars what we are using is of 16 mm dia, and the spacing what we are keeping as 130 mm center to center. So that gives you the plan of the footing, and that completes the design of square footing. Thank you.